Hi everyone, today I'll be presenting my work titled Multiscale Training of Convolutional Neural Networks, which was recently published in the journal Transactions on Machine Learning Research. My name is Shadab Ahmed and this is a joint work with Nilufer Zakariai, Eldad Haber and Moshe Eliasov. In this work, we address the central problem of training convolutional neural networks on high-resolution images more efficiently, but without sacrificing accuracy of these models and doing so in a mathematically principled way. This work combines ideas from several older concepts such as multilevel Monte Carlo and numerical multigrid methods. So let's start by formalizing the problem. Here we consider a supervised learning task where we want to learn a mapping from input signals to the outputs. In this work, we consider image-to-image restoration and translation tasks such as denoising, deblurring, inpainting and super resolution. But instead of thinking of these images purely as tensors, we would like to think of them as discretizations of the underlying continuous signal. We denote the discretization with a lowercase letter h. The learning process then becomes minimizing the expected value of the loss function L between the outputs of the neural network f parameterized by theta and the corresponding target variables yh, which are also discretized on the same resolution h. The important point to note here is that the network parameters theta are independent of the resolution, which means that the same convolution filters can operate on all resolutions regardless of how fine the grid is. However, the computational cost of training the model using gradient descent methods is not resolution independent. As h goes to 0, the number of pixels increases dramatically. For example, in 2 dimensions, halving h increases the number of pixels by a factor of 4. So although the model parameters stay the same, the cost of evaluating the loss and its gradient can explode because the expected value of the loss is computed using Monte Carlo estimates for a batch size n. This means that to have a low noise estimate, one needs to use a large batch size n at high resolution, thereby making the training computationally very expensive. As mentioned in the previous slide, to compute the expected value of the gradients, we approximate the expectation using Monte Carlo sampling. The upper bound of the error for this estimator scales as 1 over square root of n. The dominant cost in CNN training on high resolution data is not model size, it is spatial resolution of the images. Evaluating the gradient at fine resolution is extremely expensive. For example, doubling the image resolution in 2D quadruples the number of pixels, which means 4 times the convolution cost. And because the memory is limited, we are forced to train using small batches, which might make the training noisy and slow. So in this work, we pose the question, can we reduce the number of fine resolution gradient evaluations during our training? So here's the key insight. Instead of estimating everything on the finest mesh, we use a hierarchy of resolutions going from H1, which represents the finest mesh, all the way to HL, which represents the coarsest mesh. We express the expectation of the fine scale gradient GH1 as a telescopic sum of coarse gradients plus correction terms. This idea comes from multilevel Monte Carlo. For this case, the coarse level captures most of the structure, whereas the error term becomes smaller as resolution increases. In practice, we approximate each term in the telescopic sum using a different batch size. We use a larger batch size at coarser levels because they are cheap to compute, whereas we use smaller batches at fine levels because they are more expensive to compute. This gives rise to our Monte Carlo estimator for the problem, and which we call multiscale gradient estimation algorithm, which is the central contribution of our work. For this method to work, we need gradients across scales to be consistent. Under mild assumptions of boundedness of the gradients and Lipschitz continuity, we can prove the following identity. This identity states that the discrepancy between the gradient estimates on the image of resolution h versus the image subsampled on the resolution 2h scales linearly with the mesh size h. To check out the detailed proof, please refer to the appendix A of our paper mentioned in the footnote of this slide. And furthermore, these assumptions are natural for convolutional neural networks applied to image restoration problems. That is because convolutions are local operators, nonlinearities are Lipschitz continuous, and loss function that we use in our work are smooth and Lipschitz as well. Moreover, natural images and restoration tasks involve signals that are piecewise smooth, so subsampling does not introduce arbitrarily large perturbations in the gradients. Finally, we can combine the Monte Carlo error at each level with the cross-resolution bound. We get this total estimator for a multiscale framework with L levels. The key observation in this is as follows. As h goes to 0, the correction term shrinks, so coarse levels dominate the variance and fine levels require fewer samples. Meaning NL is the largest batch size, followed by NL-1 all the way to N1, which represents the smallest batch size on the highest resolution subset of images. Now, another important theoretical contribution of our work is understanding which subsampling strategy to use for multiscale training. In deep learning practice, people often use cropping of images for computational efficiency, but in our work, cropping actually breaks multiscale consistency, as we can see in these expressions. So for coarsening, the gradient error vanishes as resolution increases, which is represented with the error O of h. Whereas for cropping, the error remains constant and is independent of mesh resolution. Hence, cropping-based subsampling strategy is not theoretically consistent with a multi-level training. The derivation for these results are also presented in the appendix of a paper. Having reduced the cost per iteration, we would like to now introduce the full multiscale training algorithm, which also helps us to reduce the number of iterations. Here, we first solve the optimization problem on a coarse mesh. We then use that solution to initialize the next final level. We also prove that the number of iterations needed to reach a specific accuracy epsilon scales with coarse resolution. Since resolution halves at each level, the number of iteration also halves. As a result, in this work we reduce both cost per iteration as well as the number of iteration themselves. Now let's move on to our empirical experiments. We measure training compute using work units, which is defined as one fine resolution forward and backward pass through the network at the finest resolution. In this work, we evaluate our methods on 4 canonical tasks, which are denoising, deblurring, inpainting, and super resolution, using various neural network architectures such as UNet, ResNet, and ESPCN. The multiscale and full multiscale training strategies significantly outperform single-scale training in terms of computational costs, as measured by the work unit, and with nearly no statistically significant loss of accuracy. Moreover, as predicted theoretically, the coarsening-based subsampling also outperforms algorithms that use only cropping or a mixture of cropping and coarsening during training. Hence, multiscale and full multiscale training significantly reduces training computational load by a factor of almost 4 to 16, and the performance is often statistically indistinguishable from a single-scale training. Here's a figure comparing the qualitative results for single-scale versus multiscale training across different tasks such as denoising, deblurring, inpainting, and super resolution. Please check out our paper for more such qualitative figures. Visually, the reconstructed images are comparable across different methods of training, and we are not sacrificing on perceptual quality either. Our work also has some limitations. We develop a theory for local operators, which are convolutions. Hence, our method is not directly applicable for architectures that employ global attention, such as transformers. A newer theoretical insight might be needed to extend this multiscale training strategy to transformers. Additionally, our current implementation runs sequentially across scales, but each level in the multilevel problem can be parallelized independently across GPUs, offering further computational gains. So in summary, we introduced a theoretically grounded framework for the multiscale training of convolutional networks. Our multiscale training significantly reduces computational costs as compared to single-scale training, and we empirically validated this on several canonical computer vision tasks. Future work will include validating a multiscale approach to high-resolution volumetric 3D images and also extending this multiscale framework for attention-based networks. So thank you for listening. You can scan these QR codes for the archive preprint of our work as well as the associated open source codes. Thank you.